In section 18.2, we're going to talk about electric potential. This sounds a lot like potential energy, and it is related to potential energy, but electric potential is not the same thing as potential energy. And electric potential is often called voltage. So what exactly is it? Electric potential is the potential energy per unit charge. So you can think if you had the amount of potential energy that a particular charge had, and then you divided it by the amount of charge, that would give you electrical potential. Electric potential is very, very similar to height. If we're thinking about gravitational potential energy, we know an object's gravitational potential energy can be found using mgh. If we increase h, we increase gravitational potential energy. Okay, so in a very similar way, if we increase the voltage or the electric potential, we are increasing the electrical potential energy. So this electrical potential is very, very similar. If you want a way to think about it, it's like thinking about height in gravity. We know as something gets higher and higher, we know it has more potential energy and a greater ability to do work. As voltage increases, we know electric charges have more potential energy and they have a greater ability to do electric work. Formula, we would say that the voltage, the symbol for electric potential is a capital V, is equal to the potential energy divided by the charge. This quantity is scalar, and it can be positive or negative. One of the reasons we use voltage is because electric fields and electric forces are vector quantities. It's harder to work with vector quantities than scalar quantities, so we find that voltage really makes some problems much easier. The unit, of course, is the volt, and 1 volt, if we look over there, well, we know potential energy U will be in joules, and charge will be in coulombs. So a volt is equal to a joule per coulomb. There are times when we want potential energy, and when we need potential energy, we simply turn this formula around and we say the potential energy is simply the charge, the magnitude of the charge, times the voltage. So here is our formula. Like I say, we call this electric potential. A lot of times we just call it potential, but you are probably much more familiar with the term voltage. And if we're talking about electric circuits, that's the term that's almost always used. A 9-volt battery has a potential difference of 9 volts between its terminals. Now you'll remember when we talked about gravitational potential energy, it was arbitrary where you called 0, but differences in potential energy are very significant. That's the same if we're talking about electric potential or voltage. Really, that we can almost arbitrarily decide at what point we want to say there is 0 potential. and then measure other potentials relative to those. Another way we often think about potential is in terms of work. Remember, when a conservative force like gravity or electricity does work on an object, potential energy decreases. So we know that the work is equal to the opposite of the change in potential energy. So if we have an object and we move it from point A to point B, that is equal to the opposite of the potential energy at B minus the potential energy at A. Change in potential is potential energy at B minus potential energy at A, but it equals the opposite of that. So this actually works out to be that the work done moving from A to B is equal to the potential at A, negative minus a negative makes it positive, minus the potential at B. If I take that formula and I divide by Q, the charge we're talking about, I see that the work moving from A to B for some charge Q is simply that, look at the definition here, that's exactly the potential at A minus the potential at B. A useful relationship here is this idea that if we needed to solve for work, the amount of work done in going from point A to point B by an electric field is the charge times the voltage at A minus the voltage at B. This expression, the voltage at A minus the voltage at B, is usually read something like the potential at A relative to point B, the potential at point A relative to point B. In this case, if we take that same 9-volt battery, it means a 9-volt battery does 9 joules of work on each coulomb of charge that moves. We could say from terminal A to terminal B, from one terminal to the next. Okay, so in recap, electric potential is the amount of potential energy per unit charge, or it is the amount of work that is done on each coulomb of charge. Let's make that into an example. A 9.0 volt battery is connected to 2 parallel plates separated by 4.5 millimeters, creating a 9-volt potential difference between the plates. So what's this look like? So here we go. Here's one plate. Here's another plate. Down here we have a 9-volt battery. It's a positive terminal. There's a negative terminal. Take the positive terminal and connect it to one plate. We take the negative terminal, connect it to the other. This plate will become positively charged. This plate will be negatively charged. I want to label these A and B. I could say something like plate A has, how do I want to say this? Plate A is at a 9-volt higher potential than plate B. So a lot of times we tend to think that this would be at 0 volts and that plate A would be at 9 volts. It's a little arbitrary. We could say plate A was at 0 volts, then B would be at negative 9 volts. But we know there's a difference in potential of 9 volts. A is 9 volts higher than B. All right, let's answer some questions. What is the electric field between the plates? Let's think about this. We've got a lot of new information. We learned that electric field is equal to the force per unit charge. Well, I don't know force and I don't know unit charge, but it's something to think about. Let's think. They tell us I have a 9-volt potential energy. Well, 9 volts of I said potential energy and I meant potential difference. I know that the potential difference V can be written as the work per unit charge. Well, what's work? Work is force times distance. Aha! I think I can get somewhere now. Notice that if I take this formula and I look over here, what's F over Q? F over Q is my electric field strength. I get this new formula here that says the voltage is equal to F over Q is E D. That's actually always true for parallel plates that have that uniform electric field inside of them. If I want the electric field, then I have to solve, then E is equal to V over D. They tell us the potential difference is 9 volts. They tell me the distance separation is 4.5 millimeters, so 4.5 times 10 to the negative 3 meters. And I get a result of 2,000. We'll have two significant digits. I'll write it in scientific notation. 2.0 times 10 to the third volts per meter. And you go, Ms. Hughes, that's not what we learned for units. Previously, we said electric fields would be force divided by charge. That would be newtons per coulomb. So I better write, or 2.0 times 10 to the third newtons per coulomb. Turns out that a volt per meter and a newton per coulomb are mathematically the same thing. I can prove that if we want to. Let's think what a volt per meter. I already said that volts are joules per coulomb per meter. And a joule, you may or may not remember, can be found, it is a newton times a meter per coulomb divided by meter. The meters cancel out. That does equal a newton per coulomb. So electric fields can be expressed in units of newton per coulomb, that's our standard, but they also can be expressed as volts per meter, and sometimes that's convenient. All right, let's keep going. There's another part to this question. Part B says, an electron is released from rest at the negative plate. If the electric force is the only force, what is the speed of the electron? When it reaches the negative plate. The positive plate, sorry. Okay, so what's that look like? So we've got this little electron. Here, we'll put it over here. It's being released. There it is. It's a little tiny negative charge right there. And it's being released from the negative plate, and it's going to accelerate towards the positive plate. What an electron would do. Remember, electrons feel forces opposite of the electric field. So even though we could draw the electric field going this way, remember electric fields point from positive towards negative, that's the direction of the electric field. That little electron's going to feel a force in the opposite direction. This type of problem can be solved a couple of ways, but the easiest way turns out to be conservation of energy. We know that we have to have conservation of energy. We could use the work energy theorem, or we can look at it like this. When we're at the negative plate, that's our initial conditions. So that's initial, that's at the negative plate, and then when we reach the positive plate. Well, initially, all of the energy is potential because it's at rest. So this is when we're at the negative plate. This is when we're at the positive plate. So, how much potential energy? QV. How much kinetic energy? 0 because it was released from rest. So it's got QV of potential energy, it has no kinetic energy. By the time it reaches the positive plate, it has 0 potential energy, and all of its energy will be kinetic. It's just really, really very, very similar to problems we worked early in the year, only instead of having MGH for potential energy, we have QV, because now our potential energy is electrical in nature instead of gravitational in nature. All right, we're going to need to know some numbers for an electron. Q is negative 1.60 times 10 to the negative 16th, 10 to the negative 19th, changing numbers for some reason. Negative 19 coulombs. We'll need to know the mass of an electron. An electron has a mass of 9.11 times 10 to the negative 31 kilograms. Okay. If we think in terms of change in potential, when an electron starts at plate B, it's at 0 potential, and its potential increases 9 volts by the time it reaches plate A. So, we've got negative 1.60 times 10 to the negative 19. We've got our voltage difference is 9 volts. Negative 9. Let's do this correctly. Whoops. There we go. It started with 0 volts and it ended at 9 volts. And that has to equal 1/2 M V squared. It's pretty straightforward. This side's going to be positive, like I say. Remember, the potential where it began was 0, the potential where it ended was positive 9. So potential at A minus potential at B times the charge. This comes out to be, get a calculator. (1.6 times 10 to the negative 19 times 9. This is 1.44 times 10 to the negative 18th equals 1/2 9.11 times 10 to the negative 31 V squared. And now we just have to do the rest of our algebra and solve for V. And we get 1.8 times 10 to the 6th meters per second. In that very short little distance of 4.5 millimeters, the electron went from being completely at rest to traveling 1.8 times 10 to the 6th meters per second. That's using conservation of energy. I think that's the easiest way. QV gives me my potential. I started with 0. At the end, I have 0 potential. It's all been converted to kinetic. There is, however, another fairly straightforward way to solve this problem. We can use kinematics. In particular, we can use constant acceleration formulas. We know that the electron felt a force because it was in an electric field. The force that it felt would be equal to the charge times the electric field. So in this case, it felt a force equal to its charge, 1.60 times 10 to the negative 19 coulombs, and the electric field strength was 2,000, if you'll remember, newtons per coulomb. So it felt a force that had a magnitude of 3.2 times 10 to the negative 16 newtons. And of course, directionally, it was to the left, the way we drew the picture. It was toward the positive plate. In between parallel plates, we have what we call a uniform electric field. That electric field is constant, so it has a constant force. We know from kinematics that force equals mass times acceleration. So if I know that the force is 3.2 times 10 to the negative 16th newtons, and I know the mass is 9.11 times 10 to the negative 31 kilograms. I use F equals ma, and I can find the acceleration. The particular acceleration here is 3.51 times 10 to the 14th meters per second squared. All right, let's think what we know. We know that the acceleration, we know that the initial velocity was 0. We know the total displacement was from one plate to the other was 4.5 millimeters, or 4.5 times 10 to the negative 3 meters. And we know what A is. We just need a formula that lets us solve. We had a formula that said the final velocity is the initial velocity squared plus 2a delta x. That's 0, that's 2, 3.51 times 10 to the 14th, 4.5 times 10 to the negative 3, and all of that has to equal v squared. I just multiply, I take a square root, and that comes out to be 1.8 times 10 to the 6th meters per second. That's probably the harder way to do the problem, but I think it's really important to realize it's just as correct. Our answer comes out exactly the same. So that's really exciting. It's one of the things I always liked about physics. I got the same answer using kinematics, where if it was appropriate, which with constant acceleration is a perfect time, and I get if I use conservation of energy. All right, so let's keep moving along. So now that we know what potential is, and we've kind of looked at some problems involving potential, let's think about potential of a point charge. Well, we know that for a point charge, we said the electrical potential energy was K, Q, Q prime over R. That gave us the potential energy for a point charge Q prime because of another charge Q. That means that the electric potential which of course V is just equal to U over, if we divide out the Q prime, what we see is that our voltage then, our voltage is simply KQ over R. That's the electric potential due to a point charge. Notice if we go to infinity, we get infinitely far away from this charge, then the electric potential will fall to zero. The closer we get to the charge, the greater the electric potential. Okay. This does have the same units. Remember, our units here are going to come out as a joule per coulomb or volt. This is scalar, which means it can be positive or negative depending on the charge. That's really interesting. There's no such thing as negative mass. So there's no such thing when you're doing gravitational potential energy. The height is generally considered to be a positive above zero and a negative above zero. It's a little bit different here because the sign of the potential is going to depend on the sign on the charge. As you get close to positive charges, if we're looking at a positive charge, potential will be positive. But if we're looking at a negative charge, potential will be negative. This is example 18.2 out of your book. It says a positively charged particle is placed on the x-axis. So here's the x-axis. And right here, we have a charge. It's positive Q. It says the electric potential increases in the positive x direction. So if we move this way, V increases. The question wants to know, what is the direction of force on the charge? Well, if the potential is increasing as we move to the right, that means the direction of force is actually to the left. Which means it moves towards the negative x-axis. Positive charges naturally move from high to low potential. This is just like masses naturally fall from high to low gravitational potential. Now there is an important point there. Positive charges naturally move from high to low potential. They are free to move. So if this is a positive charge and the potential goes down this way, then it wants to fall this way. Negative charges naturally move from low to high potential. There's no such thing as negative mass, but if there was, then a negative mass in Earth's gravitation, if Earth was a positive mass, would naturally rise up instead of fall down. We don't have that. But it just helps to remember that masses naturally move from high to low gravitational potential, and positive charges naturally move from high to low potential. But negative charges will do the opposite. Just like in electric fields, a positive charge moves in the direction of the electric field. It feels a force in that direction. A negative charge feels a force opposite the direction of the electric field. All right, let's do something with a little more math. This is example 18.3 from your textbook. It says that we have 2 electrons. And of course, we know that they each have a mass 9.11 times 10 to the negative 31 kilograms. And they each have a charge negative 1.60 times 10 to the negative 19 coulombs. They give us a picture. Here is like we have an electron here. We have another electron over here. This distance is 5 centimeters. And this is point A. So there's my electron, and here's my other electron. In a minute, we're going to also talk about a different point, point B. And this distance here is 12 centimeters from A to B. All right, so the first question they ask us to do, it says, is find the potential at A. Okay. Potential's nice, it's scalar. To find potential, all we have to do is use regular arithmetic. I just have to add up the potential due to each one of these. So the formula for potential is KQ over R. But in this case, we've got 2 different charges, so we'll have to add those together. K, of course, is 8.99 times 10 to the 9th. Q is negative 1.60 times 10 to the negative 19th. It's very important that you put in the signs on this. And for the first charge, if we're looking at point A, it's 5 centimeters away, so 0.05 meters. And the second charge is actually the identical thing. It is also K, Q, and 0.05. Remember, R is just the distance from the charge to the point. So the distance from here to here is 5 centimeters. The distance from here to here is 5 centimeters. Just put that in my calculator, and I get that the voltage there is negative 5.8 times 10 to the negative 8 volts. So there is a negative potential at point A. Also ask us to find the potential at point B. All right, we need this distance from the electron to point B. Well, if you remember your geometry, we can do the Pythagorean theorem, but you may remember that that is one of those Pythagorean triples, a 5, 12, 13. This comes out to be 13 centimeters. So that's 13 centimeters. Problem looks exactly the same. I just have to change the distance to 13. I'm just going to for the first one, it's going to be K, Q, R, and since the second one is exactly the same, I'm just multiply that by 2 instead of writing it all over again. And I get that the potential at B is negative 2.2 times 10 to the negative 8 volts. And that's not surprising. The potential is smaller because B is farther from the charges. As we get farther and farther away from the charges, that potential, the magnitude is smaller. It's still negative. Technically, that's a larger number, but it's actually smaller in magnitude. All right, third part to this question, part B. It says, a third electron is released from rest at B. What is its speed? When it reaches A. I'm sorry, that's not what it says. That's not going to reach A. It's not going to head towards A. Sorry about that. What is its speed when it is very far from the other two charges? Okay, that kind of seems puzzling because that's kind of vague. How fast will it be going when it's really far? We can think about it with a little common sense here. Let me just, if I put a little electron right, sorry about that. If I put an electron right here, little negative electron, it's going to go that way. Remember, electrons repulse other electrons, and although it's at a negative potential, its potential will increase as it moves farther and farther away. Negative charges naturally go from low to high. In other words, it's trying to go farther and farther away. Same thing we did. Let's use conservation of energy. We know it started from rest at B. So we had the potential at B plus the kinetic energy at point B. And then what do we mean by very far away? Why do we think of being kind of infinitely far away? That's far. You can't get any farther away than infinity. Well, the potential energy that it has here is simply QV. It was released from rest, so it had zero potential energy. When it's very far away, its potential energy will be zero, so all of that will have been converted into kinetic energy, 1/2 mv squared. So, how much potential energy does it have? Negative 1.6 times 10 to the negative 19th times negative, let's see, we're at point B, negative 2.2 times 10 to the negative 8 volts. That means joules per coulomb. Equals 1/2. Again, it's an electron, so 9.11 times 10 to the negative 31 V squared. This is 3.52 times 10 to the negative 27 joules. This is 4.555 times 10 to the negative 31 V squared. When I finish the math, I get that V equals 88 meters per second. Okay, I'm going to introduce one more idea, and that's a different unit. This particular object at the end of the problem or at the beginning of the problem, either one, has an energy of 3.52 times 10 to the negative 27 joules. We know that when a charge is when a charged particle is in an electric field, it has an energy of QV. So we're going to introduce a new unit of energy, and that's the electron volt. One electron volt is the energy of one electron at a potential let's change it from one electron to one proton. Of 1 volt. In other words, it's QV. So 1 electron volt. Well, what is that charge? One proton is 1.60 times 10 to the negative 19 coulombs. 1 volt is 1 joule per coulomb. So we find out that 1 electron volt is equivalent to 1.60 times 10 to the negative 19 joules. It's just a convenient measurement of energy. Now, it's not the SI unit. Joules is the SI unit. If I'm working this problem, I have to work it in terms of joules. But if I just want to know how much energy How much kinetic energy does a proton gain moving through a potential difference of 1,000 volts? Let's answer it in electron volts and joules. So we've got the proton. It naturally goes from high. It starts off with at 1,000 volts, and it moves till it reaches some point we consider 0 volts. It moves through a potential difference of 1,000 volts. How much kinetic energy does it gain? It gains the amount of work done. It gains QV. In terms of electron volts, that's one electron charge, 1e, times 1,000 volts. It gains 1,000 electron volts. If I want to answer in electron volts, super easy if we're talking about protons or electrons. If I want to answer in terms of joules, then I can go back and rework it. It's going to be 1.60 times 10 to the negative 19 times 1,000. That's going to be 1.60 times 10 to the negative 16 joules. So an electron volt is just one more unit for energy that's used for these types of problems because it's convenient. All right, I think that takes care of electric potential. I hope I did a good job of clarifying it because it's sometimes a difficult idea to kind of get a grasp on. It's very similar to potential energy, but it's different. It's really very similar to height if we're thinking about gravity. The greater the potential is like being higher up above the ground. All right.